So guys, with the understanding that you're probably in much the same boat that I am, and you woke up this morning and said, you have got to be kidding me. Yeah? Okay. So you're familiar with the physiological idea of the flight or fight response? Are you familiar with that? So it's all about adrenaline and epinephrine and your body going, all right, I got an issue here. I got one of two choices. I can either run away from this, which frankly was my first choice this morning, and then my wife wouldn't let me run. So then we've got the fight option, which means we sort of, in a non-gender specific way, man up and just make this happen. So guys, today is going to sort of be about that, which is actually kind of horrible, because the stuff that we're going to learn about today is frankly really interesting. So this will be good, but understand, if you're in the same boat I am and you're going, oh, for the love, I just wish I was still at home curled up in my bed, understand that I would like to be there with you, only that's weird, so don't think about that. But I'm recording this. I could go to jail. I may be delirious. But guys, you're going to see this is interesting stuff. And my hope here is that we can get into this in such a way that you'll get a good amount of your homework done. So, shall we? You guys good? Okay. So, guys, with all of that said, I'll sort of guide you into the things that you should be including in your notes. And the first two slides of material are not things that you should put in your notes. So what are we going to do to kick this off? Well, guys, what I want to do is I want to go back and I want to remind you of the things that we learned in lab last time. So remember, we did the indicator lab, we did the serial dilution, we talked about pH being a logarithmic scale. So with those things in mind, here's what we now at least have been exposed to. Guys, we understand that the thing that makes an acid is simply the fact that it's got lots of hydrogen ions. So if that's true, what makes a base a base? It's not hydrogen, it's hydroxide. So guys, the presence of hydroxide makes bases bases. And then maybe you connected with this interesting idea that water is right in the middle, which is bordering on the poetic and the spiritual, because guys, the chemistry of life is all acid-base chemistry, and yet the very thing that makes up, 80% of our body is water or something like that, guys, is perfectly an acid and a base. It's kind of cool. So water is right in the middle. Then guys, as we were talking about acids and bases, we talked about this idea of the pH scale, which is the scale that we use to measure the strengths of acids and bases. It ranges from 1 to 14. Which ones are the acids? Relative to 7, are the acids above or below 7? Acids are below, bases are above. We'll talk more about why today. And then guys, we figured out that pH is a logarithmic scale that means that it moves by powers of 10. Is that all ringing true with you? Okay, so guys, today all that we're going to do is we're going to dig into these concepts in greater detail. So this is our laundry list for the day. First thing we're do is we're going to talk about what is an acid and what is a base. And you're going, wait a minute, I already know. Acids have hydrogens, bases have OHs. That's true. But what you're going to find out is that then leads to two different ways of understanding that. So we're going to talk about the two different definitions of acids and bases. Then guys, we're going to talk about what do acids and bases do when they react. Then we're going to talk about what do they form when they react. And then we're going to talk about how do we measure their strength. That's going to lead us to pH. We're going to spend some time and help you find the logarithm button on your calculator. And then we're going to call it a day. Can we make it? Are we good? All right, here we go. So guys, first of all, and this is where you need, well, not yet. You don't need to write this down. Guys, when we talk about acids and bases, it's going to be helpful for us to have some ideas in mind when we talk about acids and bases. So I just came up with some examples of acids and bases that you might be able to connect with. So first of all, this. I think most of you know that in the battery in your car, there's an acid. We call it battery acid. Huh? Clever, right? Battery acid in a battery. But guys, it's not, to a chemist, yeah, it's acid in a battery, but do any of you know what the acid is in your battery? Like what kind of acid is it? It's not hydrochloric. Do any of you know? It's actually sulfuric acid. It's H2SO4. So guys, the acid that's in our batteries is H2SO4. So what about then hydrochloric acid, right? We use it all the time in lab, but did you guys know that when you walk around in your day-to-day life, you are actually just a big jiggly container for hydrochloric acid? Guys, where's the hydrochloric acid in your body? It's in your stomach. Guys, hydrochloric acid is actually stomach acid. And guys, it's actually concentrated enough that it will burn holes in you. So why are you not burning holes through your stomach, which is made of flesh and is full of hydrochloric acid? It's not because it rebuilds it. Actually, it's not even, it'll eat the tissue. So what about this? What do they call it when your stomach does start to digest itself? Do you know? It's called an ulcer. So guys, when you get ulcers, literally what is happening is your stomach is digesting itself. So what is it that keeps you from digesting your own stomach? And interestingly, the answer is boogers. The same sort of mucus that comes out of your nose when you have a cold lines the inside of your stomach. You actually have a mucus lining in the inside of your stomach, and when that mucus lining wears away, then you get ulcers because the acid comes in contact with the flesh of your stomach and you digest yourself.
How does baking soda, like, to clean your battery?
Yeah.
Yeah,
so which has nothing to do with stomach boogers, right? But your question is good. So and we're going to talk about it next and then next again. So Landon's question is, what about baking soda? Because you've used that to clean the contacts on your battery. And what you're going to find out is the reason your contacts get nasty on your battery is because you get some sulfuric acid that leaks out. So to get rid of the sulfuric acid, you need something that's the opposite of an acid. And that would be a base. And so that's actually why that works. And we'll look at the chemistry of it in just a minute. Okay, so guys, maybe these will hit maybe a little closer to home as we think about acids. A lot of you are athletes, specifically like Lexi is a runner. I run into this all the time as a cyclist. One of the things that we do as we train as cyclists is we talk about lactate thresholds. That moment in your physiology where your body can no longer keep up with the physical demands of what you're doing, and your body literally shifts gears. So you've got this aerobic process when your lungs can keep up and you're metabolizing sugars and your body's doing its riding or running thing. But then you get to this point where your lungs can't keep up anymore and your body switches to a different physiological process, and the product of that process is lactic acid, and you just start dumping lactic acid into your muscles, and that's what makes them burn, if you've ever had that experience. Guys, this is lactic acid. It's C3H6O3. So when you go through your lactate threshold and you start dumping lactic acid into your muscles, when your muscles start to burn, that's actually what you're producing. So one more acid and then we'll sort of pull this together, because you know this one, right? Lemons, grapefruit, all of the citrus fruits contain what kind of acid? Citric acid. And guys, it's actually this, C6H8O7. So here's then the question, guys. Whether it's battery acid, stomach acid, lactic acid, or citric acid, what do they all have in common? Hydrogens, right? Hydrogen, 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 hydrogen. They all contain hydrogen, and that's what allows them to be acidic. Get the idea? Okay. Now guys, this one's a little trickier. When we talk about bases, I would guess you would struggle. Well, Landon came up with baking soda, which is a base, but I would bet you would struggle to come up with things that are bases. So let me offer you some. So this one may be surprising. Oven cleaner. Have you ever sprayed Easy Off oven cleaner in your oven and then you had to leave the house for the weekend because it smells so bad? Guys, it turns out that oven cleaner is actually a base. It's sodium hydroxide. So when you're spraying oven cleaner inside your oven, it's actually a can of sodium hydroxide. So that's a base. So guys, what about this? This is also a base, Rolaids. So guys, what kind of medicine is Rolaids? It's not an acid, it's an antacid. You guys ever heard of those things? So guys, Rolaids is an antacid. It is an opposite of an acid, which would make it a base. So when your stomach, right, this guy, when this dude's got too much acid in it, what do? Well, you pop a pill that gets rid of the acid, but if you want to get rid of acid, you need a base. So what's it made of? It's actually aluminum hydroxide. They tried to phase it out because they thought that aluminum might lead to Alzheimer's, but they've actually proved that it doesn't. They were actually going to try to get rid of aluminum cookware. Did you guys hear about that? It's about 5 years ago, where there was some evidence that Alzheimer's could be tied back to too much aluminum in your system. So they were going to try to get rid of aluminum pots and pans and get rid of actually deodorant. Deodorant contains a lot of aluminum, and so does things like Rolaids. And then they found it wasn't true and saved the aluminum industry. But anyway, so guys, Rolaids is also a base. Couple other and we'll move on. So what do you know this one? Ammonia. The stuff that you use to clean your windows and your countertops and stuff like that is also a base. And it contains NH3. And then finally this one, did you guys know that chalk is a base? The stuff that you draw on the sidewalks with, that is a base as well. And this is calcium carbonate. Yeah.
What is Clorox?
Clorox is actually slightly acidic. Clorox actually contains a substance called sodium hypochlorite. And so Clorox doesn't clean because it's a base. Clorox whitens because it contains chlorine. That's also why you can take, I don't know if you know this, it's an old Boy Scout trick. You can take Clorox and take like water out of a creek that could be nasty and bad for you. Put a couple drops of Clorox in it and you can drink it because the chlorine actually kills the critters. So yeah, but it's actually a little bit acidic. Yeah. That's my next question. Good for you, Josh. So guys, look at what Josh is already picking up on. So what did we say about acids? They all contain hydrogen. But now guys, think about what you learned last time in lab. What do bases have to contain? OH, right? So, all right, we're good with this. There's our OH. So guys, we understand that these are bases because they contain OH, and that works great. But now all of a sudden we've got ammonia and we've got calcium carbonate with this chalk, and they don't contain OH, and yet they're still basic. So what's going on? And guys, what you're going to find out is the definition of a base is not just limited to the presence of OH. And we're going to talk about this as we go on, but it's actually, Josh, the reason we need two definitions for acids and bases, because the first definition accounts for this, and the second definition accounts for all of them. So let's talk definitions. So guys, this is where you need to start taking notes. So guys, what you're going to find out is that the definition for, these definitions for acids and bases are actually named after the people that came up with them. So this was like 1850s maybe, and the guy's name is Arrhenius. Have you ever noticed that in order to be a famous chemist, you have to have a cool name? Schrodinger, Avogadro, Arrhenius. Not very many Smiths. See, Knappenberger, that would be a good name. I'm just not smart enough to do any of the good work. So guys, the Arrhenius definition of an acid and a base. You ready? Well, let's do acid first. No surprise. This you actually already knew. What do acids do? They give away hydrogens. Hydrogen ions. Make sure you put the charge. That rings true, right? So guys, what do bases do? You already know this. They release hydroxide. So this is the most general way of understanding acids and bases. Acids give away hydrogen ions, bases give away hydroxide ions. But then, guys, you can figure this out. What do they do when they react together? If the acid's giving away hydrogen and the base is giving away OH, when they react together, what do you get? Water, right? So, guys, the general reaction goes like this. An acid plus a base produces water, but it also produces salt. Now, guys, be intelligent chemists and realize that salt is not just NaCl. Remember what you learned, and we'll review this as we get you ready for SAGE. Salts are any positive and negative ion bonded together. So it's not just table salt, it is a salt. So for example, this, and it might be nice to have the example. If our acid is HNO3, which is nitric acid, which is horrible stuff, and then if our base is lithium hydroxide, well, what are they going to make? Well, the lithium from the lithium hydroxide grabs the nitrate from the nitric acid, and your salt is lithium nitrate. And then your other product is water. The hydrogen from the acid, the OH from the base, they get together, boom, there's your water. So guys, if you're really paying attention, what kind of reaction is this given the ones that you already know? Double displacement reaction. So guys, you may find that interesting and maybe even worth noting that all Arrhenius acid-base reactions are double displacement reactions. The products just always happen to be salt and water. Now guys, here's the trick. This works, but Josh pointed out an important idea that, yeah, this makes sense for a lot of the things that we understand to be acids and bases, but it's not inclusive enough to talk about everything that are acids and bases. So guys, y'all caught up with me here? Okay, so let's remind ourselves what Josh noticed. So we were good with acids, right? Yeah, we got hydrogens everywhere. Those are acids. Hey, this makes sense relative to bases. Arrhenius in 1850 would have signed off and said, yes, those are bases because they contain OH. But guys, these would have driven Arrhenius nuts because they don't contain OH. So in Arrhenius's world, these are not bases because they don't contain OH. But guess what? They are very basic. So the question then becomes, how can they be basic if they don't contain OH? Well, guys, it ended up that in order to explain this, it took two guys, and their names are Bronsted and Lowry. I would like to point out that I actually found the O with the slash through it. Paying tribute to our Swedish friend Bronsted. So guys, Bronsted and Lowry, two chemists that actually didn't even know each other. They both came up with the idea at about the same time, and so they share the name because they shared the idea even though they didn't know one another. So Bronsted and Lowry came up with a different definition for acids and bases. So acids are proton donors. So guys, look up in your notes and compare this to the Arrhenius definition. Oh gosh, that's going to leave a mark. Compare that to the right there on my IT band. Oh golly. Okay, I'm all right. Okay, all right. So as if this day couldn't get crazier. So guys, look up in your notes and look at the Arrhenius definition of an acid. Compare that to Bronsted Lowry. What did Arrhenius say an acid does? Gives away hydrogen ions. What did Bronsted Lowry say? Gives away protons. Guess what? Those are the same thing. Guys, think through this with me. So Arrhenius gives away hydrogen ions. Bronsted Lowry gives away protons. But guys, check this out. Go to your periodic table. What does it mean that hydrogen is element number 1? What is 1 proton and 1 protons are equal to what? Electrons. So guys, this is a hydrogen atom. It is 1 proton, 1 electron, and 0 neutrons. Now guys, watch this. What if we make this hydrogen atom an ion with a +1 charge? What do we have to take away? The electron, and what's left? A proton. Because it seems like that may have been lost on you, so let's make sure you understand what we're saying. Arrhenius said that an acid gives away hydrogen ions. Bronsted Lowry says that acids give away protons. But guys, hydrogen ions are protons. So how does that work? Let's do this again. So let me reset the thing. And guys, it goes like this. This is a hydrogen atom. 1 proton, 1 electron. Now, what if we want to take that hydrogen atom and make it a hydrogen ion with a +1 charge? Well, what do? We take away the electron. Now, this is hydrogen with a plus charge. And when that's the case, what's left? A proton. So guys, the Arrhenius and the Bronsted Lowry definitions are exactly the same. Arrhenius called them hydrogen ions, Bronsted Lowry called them protons, but hydrogen ions are protons. Get it? Okay, so what then about, and I just said that in words, so what then about bases? And this is where things change. What did Arrhenius say a base does? Gives away OHs. Guys, Bronsted and Lowry took it one step further, and they said this. They said bases are proton acceptors. And that's different. Until I show you something on the next slide, and then you're going to see that it's actually kind of the same. So now, guys, let's think about this through the lens of Bronsted Lowry. In Bronsted Lowry's way of thinking, what do acids do? Give away protons. What do bases do? Take them in. So guys, what does an acid-base reaction then look like? Because we're going to talk about the general reaction. So acids give away protons, bases take them in. So when you see an acid-base reaction, what's going to happen? Well, you're going to see a hydrogen go, woohoo! And it's going to leave the acid and it's going to go to the base. That's what an acid-base reaction looks like, Bronsted Lowry. But guys, we represent it like this. We say that the acid reacts with a base, and now you're going to run into some big words that we'll explain in a minute. When this happens, we get what is called a conjugate acid and a conjugate base. Now guys, let me tell you right now, in this class this year, all you've got to be able to do is identify which substance is the conjugate acid and which is the conjugate base. When you come back for AP next year, we spend about 2.5 weeks talking about the chemistry of conjugates. We're not going to do that in here. The only reason I teach this to you right now is so that when you come back for AP next year, we can go, okay guys, it's time to talk about conjugates, and at least all of you will go, oh, I remember hearing about those. Okay, so what are conjugates? Guys, I'm going to give you the definitions. I'm going to ask you to write them down. I'm not going to expect you to understand them until I show you. But let's at least create some common thoughts. And it goes like this. A conjugate acid is the thing that is formed when a base gains a proton, because that's what bases do. They gain protons. So guys, you may prefer to see it written in equation form. And it goes like this. Base plus proton gives us the conjugate acid. But guys, be careful with the charges. So why does this say conjugate acid with a positive charge? Why is the charge of the conjugate acid positive? Because it gained a proton, and a proton's positive. So the base, in picking up a positive proton, becomes the conjugate acid, but its charge becomes positive. And I know that means nothing to you. I'll show you in a second. So guys, what then? Well, and I made this into a sentence just so if you want to write it down. So guys, notice that the charge of the conjugate acid is one step higher than the parent base. The charge goes up because protons are positive. So what then about the conjugate base? Well guys, what do bases do? They release protons. So the idea is the conjugate base is bases take in protons. So guys, the conjugate base is the thing that is formed when the acid loses a proton. So you've got an acid, it loses a proton, it becomes the conjugate base. Or if you like it in equation form, it would look like this. The acid minus the proton, the hydrogen ion, gives you the conjugate base. And notice, guys, similarly here, that the charge of the conjugate base is one step lower because when the acid loses a proton, the charge goes down by 1 because the proton is positive. So guys, believe me, I know your heads are swimming right now, but I promise you, once you see this and once I show you a couple examples, you're going to go, okay, I get it. Or if not, you'll ask questions and then we'll help you get it. So guys, what I'm going to do is I'm going to show you a couple examples, actually 3. My encouragement to you would be don't write these down. What you'll see on the next slide is there's going to be 3 examples, and we're going to go through them together. But I think you'll be better served if you watch and learn rather than write. Then at the end of that, I'm going to turn it to you, and I'm going to ask you guys if you want to do more examples. And if you do, I have a whole nother slide of examples that we can do. And if you'd like to write those down, you certainly can. Or if you as a group are going, no, I'm okay, we can just move forward. So guys, this is what all of this is going to mean to you. So here's an example of an acid-base reaction. And again, guys, I would encourage you not to write it down, but here's what you've got to be able to do. So guys, let's remind ourselves. What did Bronsted Lowry say acids do? What do acids do? Give away protons. What do bases do? Take them in. So all you've got to be able to do is this. You've got to be a hydrogen detective. And how do you do this? Well, you do it by comparison. So guys, look, here we have H2SO4 and water, and then H3O plus, and then H2SO4 minus. So we've got our reactants, and we've got our products. So here's what you're trying to figure out. Which one of these 2 dudes lost a hydrogen? Because if you can figure out which one of these 2 dudes lost a hydrogen, you then know which one is the acid, because that's what acids do. So let's take a look. Did water lose a hydrogen? If water had lost a hydrogen, what would be left over? OH. And there ain't any OH over here. So water did not lose a hydrogen. Well, what about this? Did H2SO4 lose a hydrogen? Well, what if it had? It'd be HSO4. Oh my gosh, there it is. So what does that tell us? Well, guys, that tells us that this is our hydrogen loser, which makes it what? And all you got to do is write acid underneath it. But now, guys, here's the thing that's cool. If this is the acid, what does this have to be? The base. And remember when you learned that water is a base? It's also an acid. We'll talk more about that in a minute. But guys, right now, water is functioning as a base. So once you find the acid, the other guy's got to be the base. Now let's do the conjugates. And here's what you do. Go to the acid, take away a hydrogen. Whatever is left is the conjugate other guy. So if this is the acid, take away a hydrogen, the thing that is left is not the conjugate acid, it's the conjugate base. So they switch roles. So the acid becomes a conjugate base, and if this is the conjugate base, it makes HNO3 or H3O plus the conjugate acid. That's all you've got to be able to do with this, guys, is just identify the acids and the bases and the conjugates. So let's try another one. CH3COOH and water and H3O and CH3COO. So by comparison, is water losing a hydrogen? No, this dude's losing a hydrogen. So what does that make it? An acid, making water the base, and then go to the acid, get rid of a hydrogen, and whatever's left is the conjugate base, and the other is the conjugate acid. Get the idea? Okay, guys, that's all there is to this. But there's one thing that you need to write down right now, because it's a term you need to know. See this stuff right here? H3O plus. Guys, this stuff is important. This is what is called hydronium ion. You want to get this in your notes. Guys, hydronium ion is the H3O plus ion. So why is this so important that we're talking about it? And guys, the answer is this. H2SO4 is an acid. You put it in water, what does it make? Hydronium ion. CH3COOH is an acid. You put it in water, what does it make? Hydronium ion. Guys, the bottom line is this. All acids have to be dissolved in water, or else they're not acids. So when you put an acid in water, it doesn't matter what the acid is. It could be sulfuric acid, it could be acetic acid, it could be lactic acid, it could be any kind of acid. Anytime you put an acid in water, it always makes this. So when you go into lab, when we go into lab again next week, and when you spill hydrochloric acid on your hand and you're going, ow, 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 the hydrochloric acid is burning me. That's actually not true. Guys, the stuff that is burning you is actually the hydronium ion. So guys, acid burns are actually not acid burns, they're actually hydronium ion burns. Because what happens is when you put an acid in water, what the acid does is turns water into hydronium ion, and it's the hydronium ion that's the active ingredient in acids. So this is so important because this is always formed when acid is added to water, and in order for something to be an acid, it has to be added to water. So hydronium ion is like the active ingredient in acids. Okay, so guys, with that said, and we're going to come back to this in just a minute, let's do one more of these to make sure that you understand how this works. So you ready for this one? Conjugate acids and bases. Back to this game. NH3, water, NH4 plus, and OH. So let's figure out which one is the acid. Did NH3 lose a hydrogen? No, because there'd be NH2. Did water lose a hydrogen? Yeah, because it turns into OH. So what does that make water? The acid, making the other one the base. So guys, water is now an acid and NH3 is the base. But remember, well, let's do the conjugates first. So how do we figure out the conjugates? Go to the acid, take away a hydrogen. What's left is the conjugate base, and this is then the conjugate acid. So Josh, now we're ready to answer your question. Josh, way back on the third slide, said, how can NH3 be a base if it ain't got any OH? Do you see it now? NH3 doesn't contain OH, but it makes OH. And how does it do it? By stealing a hydrogen from water. So that's the answer. That Arrhenius didn't understand, but Bronsted Lowry figured out. Sometimes things can be bases making OH even though they don't contain OH, and the way they do it is by breaking water apart. They steal a hydrogen and they make OH by stripping water of a hydrogen. So there's the magic answer to how is it that NH3 can be a base. But now guys, this. Which one is it? Water's a base, right? Yeah? Water's a base? Water's an acid? Which one is it? It's both. It's perfectly both. Why is it perfectly both? Because water is HOH. And we'll talk about that in a minute. But guys, what is it that then determines if water is acting as a base or an acid? The other guy. If you put water with an acid, it'll be a base. If you put water with a base, it'll be an acid. It is all things to all people. And there's a name for that. It's called amphoteric. And this is a term that you need to know. Water is what we call amphoteric, which means it can act as an acid or a base depending on the other guy. Okay, so guys, as a result of that conversation, here's what you've got to get your arms around. You've got to understand what hydronium is and why it's important. You've got to understand what amphoteric means and the fact that water is amphoteric because it can be an acid and a base. Guys, there's lots of other substances that are amphoteric as well. The only one that you need to know is water. And then you've got to be able to identify acids, bases, and conjugates. Now it's up to you. Let's look. That's all I need to say. Let's try at least one more. So guys, let's take a look at these. I don't think you need to write them down, but here we go. So how do you get the conjugates? And guys, it's all by comparison. So looking here, we've got CH3, COH, CH4, and this. So CH3 minus. Did CH3 minus lose a hydrogen? No, because then we'd have CH2 over here, and we don't. So CH3COOH, did it lose a hydrogen? Yes, it did. So what does that make this? The acid. What does that make this? The base. So now we've got our acid and our base. So once we've got our acid and base, guys, this is the easiest way to do the conjugates. Go to the acid and take away the hydrogen. Whatever's left is the conjugate other guy, so it's the conjugate base, and then the conjugate acid's whatever's left. Okay, but now guys, notice charges. This is a good time to talk about this. The acid started out with no charge. When it lost the hydrogen, it went down by 1 and became negative. Remember we said the conjugate base has a charge that's down a step. But then guys, look at what happened to this. This started out negative, and when it gained the hydrogen, it went to 0 because its charge goes up a step. So remember with the charges, when the acid loses a hydrogen, the charge goes down. When the base gains the hydrogen, the charge goes up. Do you want to do the other two, or are we okay? You tell me. Good? Good? Okay, so we'll click through them. So guys, and again, you'll have these in homework. If you're having a hard time identifying acids, bases, and conjugates, come and ask, and I'd love to go over the homework with you. So guys, we've got one more thing to do, and we are done. We need to talk about pH. So here's the way this is going to go. I'm going to define it for you more specifically than what we did last time. Then we are going to talk about why do we even mess around with pH at all. And the answer is because it's easier, even though it seems more confusing because it involves logarithms. But once you really understand it, you're going to find it makes things a lot easier. Then guys, we're going to talk about what logarithm actually are. You understand there are things that move by powers of 10, but we're going to look at that graphically, and then we're going to figure out how to calculate pH. We'll do a couple of each example with our calculators, and then you'll work on homework. You ready? So it goes like this. What is pH? This you need to get in your notes. Guys, pH is a measure of an acid's strength focusing on the formation of hydronium ion, which is H3O+. You just learned that. For being wildly unmotivated, we're doing pretty well. There's probably a life lesson in this somewhere. You guys good? Caught up? Okay, so guys, let's see what you learned. Where does hydronium ion come from? From acids added to water. So when you add acid to water, the acid gives a hydrogen to water, and the water turns into hydronium ion. So if you're not clear on this, guys, the chemistry looks like this. You add acid to water, and it makes hydronium ion, and then we can now say the thing that's left over is the conjugate base. So really, technically, hydronium ion is a conjugate acid. But guys, what pH actually does is measure the hydronium ion concentration. When you're done writing down and underlining the word concentration, you aren't going to take any more notes on this page. Gosh. You okay? So guys, let's have this conversation then. If pH measures hydronium ion concentration, guys, what are our units for concentration? How do we measure concentration? Molarity, right? So what pH actually measures is the molarity of hydronium ion. So now the obvious question becomes, why don't we just talk about the molarity? Why do we talk about the pH of hydronium ion? Why don't we just talk about the molarity of hydronium ion? And it's a good question. But guys, the answer is because pH is easier. So let me lead you through this progression of thought. So guys, why do we use pH instead of molarity? The answer is this. And again, please don't be taking notes. Guys, even really strong acids, those acids that if you spilled them on you, you're done. Even really, really strong acids actually create pretty darn small concentrations of hydronium ion. It doesn't take a lot of hydronium ion to mess you up. So here's the problem. These really small concentrations end up being weird decimal numbers, 0.000001 molar. And those numbers are a pain in the butt to write down. So guys, what do we do in science if we've got a number with a weird amount of digits and we want to make it easier to write? Whether it's big or small, what do? Put it in scientific notation. So the idea is this, even in scientific notation, these numbers are still messy. Let me show you what I'm talking about. So guys, this acid has a hydronium ion concentration of 0.001. You spill that on you, you are a hurting kid. But that number, 0.001, is a pain in the butt if you've got to be writing it down all the time. So what do? Well, we put it in scientific notation. And now it's even worse. So what do? Well, guys, instead of that, what we do is we talk about the logarithm of this number. And when we take the log of this number that we call pH, it actually becomes 3. And that's a whole lot easier. It's a whole lot easier for us to say an acid with a pH of 3 than it is to talk about a weird molarity, or even worse, that weird molarity in scientific notation. So what then is pH? Well, guys, watch the arrow. pH is simply that number. You take the number off of the concentration in scientific notation, and that's the pH. That's all there is to it. But guys, notice that these numbers are negative. And what does it mean that they're negative? They're smaller than 1. This is a negative exponent, meaning that these concentrations are smaller than 1. It doesn't mean they're negative. You can't have less than none. You can't have negative concentrations. So the negative number, because it's an exponent, tells you that it's smaller than 1. So guys, let me show you what we're talking about. Here's a pH scale. Across the top, we've got the hydronium ion concentration. Across the bottom, we've got the pH. And then here in the middle, we've got some examples of things. So guys, let's take something with a pH of 2. That's actually stomach acid. Oh, go ahead.
Lemon juice has more acid than stomach acid.
Lemon juice has a higher concentration of hydronium ion than stomach acid. Absolutely. Yeah. So guys, stomach acid has a pH of 2. So if you know that its pH is 2, what do you now know about stomach acid? Well guys, what does this 2 represent? Watch the arrow or watch the circle. This 2 is that 2, which tells you the molarity of this is 10 to the negative second, which written out is this. So stomach acid is 0.01 molar H3O. 0.01 is 10 to the negative second, which is the pH. See the relationship? So now let's look at something that is less acidic. Let's go up here to pH 6, which is milk. Did you guys know milk is acidic? Yeah, milk is slightly acidic. So guys, what does it mean that milk has a pH of 6? Well, this 6 is this 6. And this 6 is the negative exponent of the concentration of hydronium ion. And when you write it out, it's this, 0.000001 molar. So you can see that this is less concentrated, meaning it's less acidic. So what if we go into the bases? Well, guys, let's go down here to pH 12. That's ammonia. Well, guys, what does this 12 mean? Well, the 12 is this 12, and that 12 tells us the concentration of hydronium ion is 1. Really, really, really small. So, guys, then the question is this: what makes that a base? And the answer is this. This concentration of hydronium ion is less than the concentration of water, and so where you've got less hydronium, you've got more hydroxide, and that makes it a base. I know that's kind of a weird thought. We talk about it more in AP, but bottom line here, guys, is that this number is the concentration. Get the idea? Okay, so watch this, and you're going to want to write this down. So now what we understand, and guys, watch the boxes. You now understand that pH and hydronium ion concentration are related. You understand that the pH is the exponent in the hydronium ion concentration. This is a pretty good animation. So guys, watch. How do these come together? They come together like this. And this is the equation that you need to know. pH is the negative log of the hydronium ion concentration. And if you understand logarithms, you'll understand that this mathematical expression is simply the circles that we were moving around on the board. If you don't understand logarithms at that depth, you're okay. If you just know that this number is that number, and if you can solve this equation, you'll be just fine. So guys, here's what we're going to do. We are going to solve this equation 4 times. We'll do 2 examples when we're going from pH to H3O concentration, 2 examples H3O to pH. When we're done with that, you'll have time to work on your homework. Now, if you try to do these and you can't get the right answers because you and your calculator are not yet friends, I don't want to try to answer those questions corporately. I'll work with you individually on how to run the log button on your calculator. So guys, we're going to solve 4 examples and call it a day. Here we go. So, well, before we do, we should mention this. Guys, these brackets right here, those are not squared off parentheses. Those are brackets, and they mean something. They mean molarity. So the number that goes in those brackets for H3O is the molarity of the H3O. Forgot to mention that. Okay, so now guys, let's do some math. And it goes like this. Please don't write down the examples. Just trust me. Ready? What is the pH of a solution if the hydronium ion concentration is 1 times 10 to the negative 4th? What's the answer? 4. Get it? Guys, that's it. That's all pH is. If the hydronium ion concentration is this, the answer is 4 because pH is this number minus the negative. Good? So what about this? What if the hydronium ion concentration is 3.6 times 10 to the negative fourth? Why is the answer no longer 4? Because this is not a 1. So now we need to do the math. And guys, I would encourage you to write this down in your notes with me. How do you solve this? First thing you do is you write down the equation. Then you plug in the molarity for the hydronium ion. Where does that go? Inside the brackets. So pH is the negative log of 3.6 times 10 to the negative fourth. Now guys, and please don't be offended, this is the only time in my life where I've actually found TI graphing calculators to be better than anything else that's out there. Typically, I hate TI graphing calculators because they're horrible with orders of operations. This is the one time where they actually work well. The reason is because in a TI graphing calculator, you can just type this in. May I borrow that for a second? So long as you remember that the negative sign that you want is this dude down here by the decimal and not the subtraction button. But if you use that change sign button down at the bottom, you can just type in, including the parentheses, negative log parentheses 3.6. And then guys, remember how we put scientific notation in our calculator, the EE button, 3.6 EE, and then negative 4 is not subtract 4, it's the change sign 4. Close the parentheses, and what's that? It's the second of that. And guys, the answer you should get is 3.4. Now, if you don't have a TI graphing calculator, guys, I can help you do this in whatever calculator you've got. So like Cody with yours, all you have to do is enter the number first and then hit log, I think. So guys, if you're using a calculator that is a scientific calculator but not the TI grapher, a lot of times what you do is enter the number first and then hit log. But if you're still having trouble getting there, I'd love to sit and help you. I'm pretty sure I can. So, we okay with 3.4? And again, guys, if you're not getting that, let me sit down with you individually and I'll help you. You good? Okay. So now, guys, let's do this. In this question, we were given hydronium and we came up with pH. Now let's go the other way. Don't write these down. Check this out. What is the hydronium ion concentration of a solution with pH 8? Don't touch your calculators. What's the answer? 1 times 10 to the negative 8 molar. Done. Yeah? But guys, what if the number is not a whole number? What if the number is something like 8.12? Well, now we need to solve it. So guys, do this with me. pH is equal to the negative log of H3O. Where does the pH go? Obviously, pH. So 8.12, and notice guys, I turned H3O plus into X. Remember that magical day in algebra when you learned you can use an X to mean anything? You felt like a god. You could just change things into X. Well, makes it easier. So let's call it X. So now guys, how do we solve this for X? First thing you do is divide by the negative 1. So move the negative 1 over. Remember, solving for X is really just the process of getting X by itself. So we got rid of the negative, now we've got to get rid of the log. So what do we have to do? Divide by log. But guys, algebraically, dividing by log is taking the inverse log. And the inverse log, which we would write like this, the inverse log is actually the 10 to the x key. If you find the log button on your calculator, you'll find that the second log, so the shift log, actually remember on most of your TI calculators it's then in yellow. You'll notice that the yellow thing above the log button is the 10 to the x key. 10 to the x is actually the opposite of log. So what you're going to type in then is second log negative 8.12. And the answer that you should get is 7.59 times 10 to the negative 9th molar. Now guys, again, if you're not getting this number, I would love to sit down and help you. But at this point, we're done. We went over acid-base definitions. We went over the idea of conjugates. We went over amphoteric. We went over hydronium ion. We talked about pH and what it means, and now we know how to solve for it. So guys, the homework that you have in front of you is actually a great summary of all of those ideas. What you're going to find is this homework is actually 3 pages long. You're doing a lot of filling in tables. Guys, I'll tell you this. When you're filling in these tables, watch out for charges. A lot of the things that you're going to be doing is writing down conjugates, and remember that the charges of the conjugates change. So 3 pages of homework. We will grade this on Tuesday. And then guys, starting on Tuesday, we are going to fall into a lab lecture rotation. Tuesday will be lecture, Thursday will be lab, Monday will be lecture, Wednesday will be lab, then lecture lab. We're just going to alternate lecture lab. So guys, with the last 5 minutes, I'll give you your test back. All the answers to these are on the wall. I'll bet you if you get to work, you can get all 3 of these pages done and not have homework over the weekend, which would be a beautiful thing. Absolutely, it's all in your notes. Yeah.
I have questions on all my questions.
Hold on, let me stop recording.